a number of interesting parts of number theory. So this question is, so this is called the sum of the reciprocals of the primes. Okay? So what this sum here represents is adding up 1 over p for every prime p. Okay? So this sum is, in number theory, anytime we see the symbol p, we mean a prime number. That's the convention. So the beginning of this series anyway looks like this. Okay, you keep going. Now we already know from our study of number theory that there's an infinite number of primes, don't we? Okay, we proved that quite a few, well, 2 or 3 weeks ago, that there's an infinite number of primes. So this sum we already know is an infinite number of terms. So the question is, does this sum come to some value? Does it converge to some finite value? Or does it diverge? Okay, so that's the question. Clearly, if there was a finite number of prime numbers, you'd just be adding a finite number of fractions like this, so it would just have some value. And if you could identify all the prime numbers, you could have them all at once. Okay? But we already know that there's an infinite number. But actually, the work we're going to do today, the way we're going to study this sum, doesn't make that assumption. So we're going to, for the purposes of this class, we're going to be a little bit agnostic on whether or not there are an infinite number of prime numbers. Well, first of all, before we start investigating the behavior of this series, it reminds us of one that we investigated last year in the mathematics fundamentals course. Okay? I mean, what famous series does that remind you of? Anybody know which series I'm referring to? Begins with a H. No, really. An important example of a divergent series that we met in maths fundamentals last year. That was related to it. Yeah, there was a more general class of hyperharmonic series. But I'm referring here to just the harmonic series. Yeah, remember? So this reminds us of the harmonic series, which was the sum of 1 over n, taken over all the positive integers. N equals 1, 2, 3, 4, 5, 6, and so on. Now, what did we find out about this series? We proved that this series was a divergent series. One quick way you can see this. So this is what this series looks like, and we had a quick kind of argument for this, which was based on bracketing the terms, grouping the terms together, leave the first 1.5 alone, then group together 1/3 and 1/4. That's 2 terms. Then group together the next 4 terms. Then group together the next 8 terms. Then the next 16 terms, and so on. And you see, instead of 1/3, I'll replace the 1/3 with 1/4. And I'll replace each of the things in the next bracket with an 8. Sorry, this is extremely bigger then. So I'm replacing things by things that they are less than. Yeah, so I replace 1/3 with 1/4, makes the whole thing smaller. Replace 1/5 with a 6, 6 with a 8, sorry, 1/5 with an 8, 6 with an 8, 7 with an 8, and so on. So you're making the whole series smaller. But this series is 1 plus 1/2 plus, well, 2/4 is a half, 4/8 is a half. The next bracket I would have would be 8/16, which is a half again. Okay. So when you look at the harmonic series and you group the terms like this, what you see is that if you wait around long enough, you keep seeing halves being generated in the infinite series. It takes longer and longer for them to generate halves. You need to accumulate 2 terms for the first half, 4 terms for the next half, then you'll need 8 for the next half, and then 16 for the next half. So you need more and more terms, but it's an infinite series. There's an unlimited number of terms. So if you keep seeing halves being generated, that means this has to be divergent. Okay? If you keep generating halves, you can get to any value whatsoever. So this shows that the sum of 1 over n diverges. Okay, that was an important result for us about the harmonic series, that it was a divergent series.
You know what you heard equal to?
Yeah.
That's accepting that, isn't it?
That's what? Yeah, so when this equals here means the previous line is equal to this.
But that previous line, how do you get that?
Sorry?
That previous line.
This line.
Yeah.
This line, I replaced each, so the rule is in each bracket, you replace every term in the bracket by the end term. So I replaced a third with a quarter. A quarter is smaller than a third. So this is why this new expression is smaller. And here, a fifth, I replace all of these with an eighth. So you got 4 eighths. And then in the next bracket will go from 1 over 9 to 1 over 16. 8 terms, and I'm going to replace them all with sixteenths. So they'll be 8 sixteenths, which will be another half. Okay. So this shows that the sum 1 over n diverges. So when you add up the reciprocals of all the positive integers, you get a divergence series. So the question is, if you see this series up here is a subset of this one, if you like. Okay? Because the series we're aiming for, you're only adding up the reciprocals of all the primes. So that series, if this is divergent, well, maybe that one could be convergent, or maybe it's still divergent. It could go either way. Now, when I said it was going to be a fun lecture for that, part of what I was referring to was that we're going to, the first proof of this that we're going to show is based on the original proof of this, which was the proof that this series actually diverges, which is due to Euler from the kind of 18th century about. And the reason I say it's fun is that it takes some liberties. Or the reasoning I'm going to put down here is a little bit non-rigorous, a bit exciting. We won't obey all the usual rules of rigor, but the ideas we'll be expressing are still correct and can be made rigorous and can be given a complete correct proof. Okay, so we're going to prove. So we have a theorem that the sum of 1 over p diverges also. And when you add up all the reciprocals of the primes, you also have something divergent. And we're going to prove that it's divergent by comparing the behavior of this to the behavior of the harmonic series. Okay. We begin with so this is going to be a proof, but a non-rigorous proof. Yep. P is, well, the convention, if we're in number theory, is that whenever we see P, it represents a prime number. So this means just summing over all the primes, the quantity 1 over P.
Starting from P.
No, starting from the first prime and proceeding through all of the primes. First prime being 2, so it's a half plus a third plus a quarter. No, sorry, half plus a third plus a fifth plus a seventh plus.
So what is P prime?
Well, I could write the same thing here. So it means the sum over all P, which is prime.
Oh, right.
Yeah. Sorry. Yeah.
So the first prime number.
No, this is just the. You see, if I don't show you the subscript, if I just write sum of 1 over p, the question is, well, what is p? What things am I summing up? Well, it starts. This sum is going through all the primes, starting with the first prime, which is 2, then the next prime, which is 3, then the next prime, which is 5.
But isn't it already established that 1 over p?
Sorry?
Isn't that already been established by saying 1 over p, 1 over p, 1 over 1?
Yeah, you could just understand the sum of 1 over p to mean the sum of 1 over the prime. Yeah, I'm just confirming, just putting extra information. Just restating it. So this is the sum we're talking about. The sum of the reciprocals of all the prime numbers. Okay, and we start by a nice observation. That if you want to add up all the reciprocals of the positive integers, you can do it by multiplying together all these things. Now, what's going on here? For every prime p, I'm considering this infinite sum. Okay, this is another infinite sum. 1 plus 1 over p plus 1 over p squared plus 1 over p cubed, and so on. So it's the infinite series of positive powers of 1 over p. And I'm considering this bracket for every prime number p. I've got an infinite bunch of these brackets, and I'm going to multiply them all together.
So should we be writing 1 over p above n?
Sorry?
You know, on the left-hand side, should we be writing 1 over p
No.
above n?
No. The left-hand side, I have the normal harmonic series here. Okay? And the reason that this equation is true, or the reason that it makes sense to write it like this, is when you take the product of all these brackets. I mean, how do you multiply together a bunch of brackets? And if there's loads of terms within the brackets, well, you have to form a lot of products. From each bracket, you have to take one term from each bracket. So to generate all the terms on the right-hand side, from each of this infinite collection of brackets, you have to select one item from each bracket. So one item from the first bracket, one item from the second bracket, and so on, and multiply them all together. So when you do that, you see that you can achieve what you get when you multiply something from this bracket with something from the next bracket, something from the next one. You're going to get 1 over a product of prime powers. But we know from the fundamental theorem of arithmetic that every integer can be written as a product of prime powers. So this infinite product here will generate all of the reciprocals that look like 1 over a product of prime powers. So therefore, it'll generate 1 over every positive integer. Since by the FTA, fundamental theorem of arithmetic, the right-hand side contains all reciprocals of powers of products of powers of primes. I.e., all 1 over n for n greater than or equals 1. Because suppose I want to see where is the term 1 over 15 going to come from? So 1 over 15 is a part of the harmonic series. Well, what I do is I just choose the element 1 from all of these brackets, except for the one corresponding to p equals 3, I'll take a third. and the one corresponding to p equals 5, I'll take 1 over 5. So I'll take the element 1 from every bracket, apart from 1 over 3rd from the p equals 3, 1, and 1 over 5 from the p equals 5, 1. So when I multiply all those 1s, that infinite number of 1s together, and the 3rd by the 5th, you get 1 over 50. And you can do the same for any integer. Whatever 1 over n you want to find, you just look at the prime factorization of that n, and you choose 1s from every bracket over here, except the ones corresponding to primes that are in the prime factorization of n. From those brackets, you choose the appropriate power that p appears to in the prime factorization. When you multiply them all together, then, you generate the 1 over n. But when you look at one of these brackets on the right-hand side, we should also recognize that it's an infinite series. What kind of series is that? There's a certain word that goes before series. This is a
Power series.
well, yeah. Something else, so? Not hyperharmonic. Yeah, it's the powers arising, but the p is staying the same. And we maybe not call it power. A power series is where you have a function depending on a variable x, say, which is defined by an infinite series. But this isn't a function. There's nothing undetermined here. So, like for instance, if you had p equals 2, you'd have 1 plus a half plus a quarter plus an eighth plus a 16th and so on. What kind of series is that? It has a certain name.
Geometric. Geometric series.
Geometric series. Each of these series and each of those brackets is what's known as a geometric series. Okay, this is more maths fundamentals. Remember, a geometric series has a certain initial term, and then every subsequent term is generated as a fixed multiple of that initial term, of the previous term. So the first term is 1, second term is 1 over p, the next term is 1 over p times the previous term, 1 over p squared.
Constant ratio.
Sorry? A constant ratio of 1 over p for this series, exactly. Yeah?
What have you written there? Since by a... What did that say there?
Since by the fundamental theorem of arithmetic, the right-hand side contains all the reciprocals of products of powers of primes, i.e. all the 1 over n for n bigger than or equal to 1. So this is the geometric series, the sum of a r to the n minus 1, from n equals 1 to infinity, where a is equal to 1 and the r is equal to 1 over p. Well, we know what that is equal to. So we also know from maths fundamentals that we have a complete description of geometric series. There's a summation form. Anybody remember what that geometric series sums to? There's a nice formula in terms of the a and the r for the infinite sum. Well, it's a over 1 minus r. If it is convergent, and that it's convergent in the case where the r has absolute value less than 1. And this certainly is absolute value less than 1, because it's 1 over a prime. Well, in that case, it's just equal to a over 1 minus r. So then we get this really nice result that the harmonic series is equal to the infinite product of 1 over 1 minus 1 over p. You take that factor for every prime, p, and you multiply them all together. Okay? Because each of these brackets is a geometric series which has this sum, a over 1 minus r. Okay, so we've been a little bit non-rigorous in what we mean about an infinite product. You know, there are some hurdles to get over to make this well defined. to make an infinite product of brackets, each of which has an infinite number of terms in them. To make that well defined, you have to proceed very carefully. But taking it and running with it, we get this nice expression here. And now we can start to build our proof that the sum of 1 over p diverges. So from this formula, we proceed again non-rigorously, highly non-rigorously. I'm about to do something which I normally would not do in front of children. In this context, of course, I'm the adult. You're in the childlike position because you're students. So normally I wouldn't do this because strictly speaking, it's a little bit, you shouldn't show young people this. I'm taking the logarithm of the harmonic series. Now, what's the problem with that? Why is that? Why shouldn't you show that to inexperienced people? Because well, it's playing fast and loose with some of the rules. Because okay, the logarithm is a function defined for real arguments, but we know. I mean, I just showed you. I just reminded you at the top of the page what we did last year. We know that this series is divergent. It doesn't have a value. Or if you do want to attach a value to it, you have to say it's equal to infinity. You shouldn't really take the logarithm of it. Strictly formally speaking, you shouldn't take the logarithm of it because you don't have a definition for it. This isn't referring to any number. So you shouldn't go ahead and take the logarithm. Why would we? Because the last day of term, you're feeling adventurous. And this, well, early mathematicians, so people from Euler's time, this, they hadn't fully developed all the notions of mathematical rigor that we use today, and the very formal, careful way that we've set up for talking about infinite series. So they this is a bit, they acted creatively. This is a bit of kind of creative mathematics. Suppose we could take the logarithm of an infinite sum. I mean, there are ways to make it make sense, but we won't worry about those for today. But lying behind it are some correct ideas. So, but strictly speaking, everybody should walk out at this point, because what does logarithm of infinity mean? But let's suppose we can do it. Now, what happens when you take logarithm of a product? What do you get?
The sum of the
When you take a logarithm of a product, you get the sum of the logarithms. Right? So logarithm moves inside the product, and the product turns into the sum. And what happens when you take the logarithm of a reciprocal, like that? 1 over something? Another property of logarithms? Sorry? Minus, yeah. The logarithm of 1 over this is equal to the logarithm of the denominator, except minus the logarithm. So our logarithm of the harmonic series is equal to this minus the sum over all primes, the logarithm of 1 minus 1 over p. And now we make use of a Taylor series expansion for the logarithm. So you can look up the Taylor series expansion for the logarithm of 1 minus x. So I'll put this to the side. The logarithm of 1 minus x is equal to, better get this right, minus 1 over, sorry, minus x minus a half x squared minus a third x cubed, and so on. That's the Taylor series for the logarithm function. Okay, now this would only be valid, I think, for x less than, yeah, for x less than 1, or absolute value of x less than 1, I think. But we're certainly in that case here, because we're talking about 1 over p. And this minus sign at the front turns them all into positives. I've still got my sum of p, but instead of logarithm of 1 minus 1 over p, I have now this sum. 1 over p is 1 over 2p squared, is 1 over 3p cubed, is 1 over 4p4, etc. And look, here we have it. Here we have the sum that we want. This is the sum of the reciprocals of all the primes. We've also got in here the sum of all the reciprocals of the squares of primes, and the sum of all the reciprocals of the cubes of primes. We scale by half a third. So, well, I've done the Taylor series to get this to pop out, to get the thing I want to pop out. So the Taylor series is applied here when I replace the logarithm of 1 minus 1 over p with this infinite sum of 1 over powers of p.
What the minus? Before the, yeah.
But see, each of these have a minus. All these coefficients are minus here.
Oh, so it's
So this minus in the front turns them all into positives, yeah? Okay. So here it is. Look, that's the thing we're interested in. That's the thing we're interested in, and over here, for the rest of the terms, okay, you've got from here this plus this plus this. Well, I can factorize out the 1 over p squared, and then I've got a half plus 1 over 3p plus 1 over 4p squared. Then you'll have 1 over 5p cubed, etc. Let's just doing a bit of algebra, or a bit of, manipulation of the sum. And this thing nearly looks like a geometric series again. Nearly does, but it's complicated by these half and third and fourth and fifth and so on. But I can get rid of all those. So instead of writing a half, I'll write 1. Instead of writing 1 over 3p, I'll just write 1 over p. Instead of writing a quarter p squared, I'll write 1 over p squared, and so on. Oh, there's this 1 over p squared here. That's the same one that was there. But that's our geometric series. Geometric series has a finite value, a over 1 minus r. So that's your 1 over 1 minus p again. So, and of course I'm making something bigger. So I'm placing a half with 1, a third with 1, a quarter with 1. So I'm making this thing bigger, but this is now equal to the sum of the reciprocals of primes, the sum over all p, 1 over p squared times 1 over 1 minus 1 over p, again using the geometric series formula. And then just multiplying in the p squared in the denominator gives me p squared minus p here. So what have we got at the moment? We've got that the logarithm of the harmonic series, which, you know, really strictly speaking, we shouldn't talk about. But if we allow ourselves to talk about the logarithm of the harmonic series, it seems to be equal to the sum of the prime harmonic series plus this infinite sum. Now this one, you see this prime harmonic series you think about comparing to 1 over n. This prime series you think about comparing to 1 over n squared. And by comparison with the sum of 1 over n squared over all integers n. Now this one we know to be convergent. From our maths fundamentals work last year, you can apply the integral test to the series 1 over n squared and you'll find that it's convergent. So by comparison with sum of 1 over n squared, this term converges. So it's converges. It's just equal to some finite number. So in conclusion, what have we done? What we've done is we've said the logarithm of the harmonic series is less than the prime harmonic series plus a constant. Okay, so we can take this constant c to be the value of this sum here. I know it will have a fixed value because it's a convergent series. Okay, we'll just justify it like this because it compares to the sum of 1 over n squared, which we know to be convergent. Okay, we proved that was convergent last year. Sum of 1 over n squared. Sum of 1 over n squared is convergent, so the sum of 1 over p squared is going to be even more convergent because you only add up 1 over n squared when n is a prime. But what does this looking at this conclusion statement, the summary statement, this gives us the answer, right? Because here's our prime harmonic series that we're interested in. And we're saying that the logarithm of the harmonic series is less than it plus a constant. But as we said before, what kind of numerical quantity have we got on the left-hand side? We've got the logarithm of a divergent series. It can't be strictly less than some finite thing plus another finite. Because this is the logarithm of the harmonic series. The harmonic series grows and grows without any upper bound. So if you take the logarithm of it, you're also going to have something that grows and grows without any upper bound. Infinity in a sense. And how can infinity be less than something plus a finite number? Well, the only way that could happen is if this was infinity itself as well. Okay. So it's kind of like a proof by contradiction. This can't be finite. If this series here was convergent, this would just be a finite number. So you'd have a finite quantity on the right-hand side, but the logarithm of the harmonic series on the left-hand side, being bounded above by that finite. Well, strictly speaking.
So,
But what lies behind this, I mean, you can fix this argument. You can make this argument rigorous and give.
So you could almost say like say even though they didn't apply, if it did.
Yeah, but it does apply in a sense because there are some the ideas behind this are correct. Linking together the behavior of all the integers to this quantity here, 1 over 1 minus 1 over p. That is a correct idea.
So would you accept it?
It depends what the context was. If the question was, no, again, this is not examinable. We're just doing this out of interest the last week of this term. But if the context was, you know, give an exposition of Euler's argument for the divergence of the sum of reciprocals of the primes, then this is it. So it's like, it's maths from a few hundred years ago, which doesn't meet all the rigorous requirements of some of our formal presentation of maths today. So it's interesting to look at. It's not a mistake. There's correct ideas behind it. So this shows that the sum of p, the sum over p of 1 over p is divergent, since the left-hand side is divergent as well. The left-hand side of that inequality. So this argument is based on work of Euler. Sometime in the 18th century. It can be fixed up and made rigorous. But what we do see here is, you know, some of the themes of the connections between number theory and analysis, because we're linking concepts in number theory, the behavior of the primes, to concepts in analysis, to convergence of infinite series.
What makes a proof rigorous or non-rigorous?
Well, it's what makes it non-rigorous if you take the logarithm of an infinite quantity, for instance. So, yeah, where you don't stick strictly to full definitions and correct reasoning, correct logical reasoning. So the main, all the manipulations are correct, but just the main question mark is how can you build an argument on taking the logarithm of an infinite sum, which is divergent. And while we know that the logarithm of a product is the sum of the logarithms, well, we know that for finite products, like the logarithm of a times b is the logarithm of a plus the logarithm of b. The question of whether that extends to infinite products as well is this maybe should be justified further. But so there is lack of rigor here. Things need to be fixed up and fully justified here, but there's no mistake. There's no mistaken reason there. It's essentially correct. So what was I writing? I was this argument is based on work of Euler. It can be made rigorous by today's standards. I mean, the way that is done is rather than talking about taking the logarithm of a divergent infinite series, instead have to rephrase everything in terms of behavior of partial sums and talking about the long-term behavior or the divergence of the sequence of partial sums and so on. So you can fix it all up and make it more rigorous. But it shows some of the early connections between number theory So our experience with number theory so far, we started with the integers, looking at divisibility of the integers and so on, and doing induction proofs. It's all very discrete. We weren't dealing with anything like calculus or real valued functions and so on. But here, where we started talking about the behavior of infinite sums, using the logarithm, using Taylor series, there we're starting to use concepts from analysis, which you kind of early on you think is a kind of wholly different field of mathematics than the discrete nature of the study of the integers and divisibility on the integers. But this argument is showing that there seem to be some strong connections between the two. So this shows some of the early connections between number theory and analysis. Okay, concepts like infinite series, Taylor expansions, and so on. So one of the sub just resting the laptop on it there, but one of the subfields of modern number theory is analytic number theory. So this is Apostle's book, which some of the stuff in this unit is based on. So analytic number theory is where you take these ideas and you apply them to their maximum. You use lots of analytic tools, chiefly complex analytic tools. So you look at the behavior of functions defined in the complex numbers and the complex analytic properties they have to do with integration, differentiation, using those tools to prove things in number theory. And there's a whole other field of number theory called algebraic number theory, which doesn't do that at all, but instead focuses on number theory via the more kind of discrete nature of things like groups and fields and rings, algebraic objects. I'm not talking about analytic things like calculus and Taylor series and so on, but taking a more discrete approach. Those are the two broad themes of analytic number theory and algebraic number theory. Just seeing some aspects of there in this informal argument. Okay, then I hope you enjoyed that. I hope it sparked your interest in it. Later on, if we've got some time in turn 2, I might show the rigorous argument, or show you.